Hey everybody, and welcome to the 2021 Hackaday Remoticon. I'm Elliot Williams. I'm managing editor of Hackaday. This year we've got 3 keynotes, not 1, not 2, but 3, and they span software, hardware, and hard science. First up today, we'll start with software, or should I say firmware, because our speaker is Elecia White. She is an embedded engineer extraordinaire. She's written the book on it, basically. She's written Making Embedded Systems. She's held down the Embedded FM podcast for a very long time now. And we are super happy to be able to share her hard-earned expertise with you to help guide you through one of the really dark corners of microcontrollers, the memory map. And so without further ado, I would like to present you Elecia White.
So happy to be here, and thank you for that introduction. Let me share my screen. Okay, if you are not seeing what looks like the first slide in a slide deck, I don't know, none of you can talk, so here goes. I am here to talk about map files and memory, and as Elliot said, I have a podcast and a book. I've been an embedded software engineer for a couple of decades. I've been thinking a lot lately about how we teach things. I'm working on an online course about developing embedded software professionally. And there were so many lectures. I'd start with grand ideas of explaining bootloaders and pointers and state machines, and it would all be glorious and fun, like my talk about map files. And at some point, bleary-eyed and frustrated, I would think, look, not everything can be as fascinating as map files are, which when I say it aloud sounds ridiculous. But let me share my view of memory maps with you, and then we can figure out how to make the rest of embedded systems more fun to learn and to teach. And if you don't know where a map file comes from or how it's built, stick around, we will get there. Before that, I want to show you how awesome they are and why it's worth digging through your folders to find the file. Map files show you the memory layout of your system. They depend on your compiler, linker, and processor. And what I show you won't be exactly what you see on your system. I want to give you landmarks to look for. I want you to have a map for exploring your own map file. There are many ways of looking at memory layout in your microcontroller system. Some are here, but let's look at my favorite a little more closely. On the left, you can see how much we have of each type of memory. My system here is a simple chip, just 2 types, flash and RAM. And this is the sort of memory layout on the left that you might find in your processor's data sheet. On the right is where I've put the memory, what I've put into the memory. I've drawn it out in rows so I can see the ordering and what touches. There's my code, the constants, the initializers for my globals, some memory to grow into, a little flash storage block, maybe more like a database than a file system, but someplace to keep my serial number, security keys, and manufacturing data. And since I want to be able to change my firmware, I have a fixed bootloader to do that. In RAM, I have actual globals, a heap for any dynamic memory allocation, and a stack. With an RTOS, an operating system with multiple threads, I'd have multiple heaps and stacks. I like looking at memory this way. It's worth sketching out early in the design to make a plan about where things will be and to set expectations about how much code you can put in your processor. But these are big sections, the bird's eye view, and they don't let us dig into what we need when we get to the implementation stage. So why do we need more detail as we do development? Map files can help with lots of problems. They're tools, amazing tools to help you solve these problems. But we'll get back here in more detail. First, let's walk through an actual map file. I want to look through an example program called Hello. This is for a TI chip that can use BLE and Zigbee, and it was compiled with Code Composer Studio. It uses TI's RTOS, which is called BIOS, and it has a main that prints hello world and exits. Now, there's a bit more going on with the init so that our system printf actually goes someplace. And then there's the operating system piece, BIOS exit. And it looks simple, but it's an embedded system. Even printing hello world isn't really simple. I'm going to switch over to the map file now. And having someone else scroll through this would be tough for me. So if you want to scroll at your own speed, you can find these files on my website at embedded.fm, or I dropped them into the Discord link for those of you watching live. And for those of you who know a bit about map files, I'll put the linker file on the right so you can see if you can connect them. But if you're here for map files, ignore that window. So let's take a look at this map file for a moment or two. It's a wall of hex. It's not nice looking. Reading some of it, the memory configuration, so far so good. Flash and RAM, GP RAM has attributes like flash, and the name says RAM, so probably some sort of RAM. We could look it up, search on Google, the processor name and GP RAM, and discover it's a cache. But right now, we don't care. We just want a bit of orientation with this map file. The segment allocation map, it's not a good name. Better to think of it as a summary. We can look at what these addresses really are. This is flash. We know that from the address. Right above, it says 00 is flash. It has different data segments, text, const, CINIT, reset vec. You can guess what these are, or maybe Google them, though I'll warn you, text means code, because we're going to see that a lot, and it's important. We can also see where our RAM is. Again, just based on the address. This has different segments as well. Data, heap, BSS, data again, stack. Heap and stack make sense. BSS and data we'll see a lot more of. As I scroll down, these things get broken into more and more detail, zooming in on the contents of the different sections. And don't read everything. Look mostly at the left side of the screen with the sections. And wherever there's a bit more white space, like here, expect something to be a little more interesting. With BSS and data, these are in RAM. For either one, if we looked at the symbols on the right side when they were on the screen, and we wrote this code, we might see a global variable name we recognize. But let's go on to text. These are going to be function names. This is where your code really lives in the chip's flash. The first column is the start address. The second column is the length of that function in flash. If you get a crash and your backtrace says it was at 300, 000000300, looking here, we can see that it must be in the power sleep function on line 157. Scrolling down, this goes on for a good long time. And I have to wonder how much of this we don't really need to run. How many bytes of flash we could get back if we needed them to do more useful work. Oh, 353, something new. White space really does make this easier. These are constants. For example, line 365, board GPIO init table. This is a piece of memory that sets up the GPIO on init, and in the source file, it's marked with the const keyword. That's all this is. It's not magic. So we're getting down to the module summary, which takes objects of each type of memory, read, write, read only, code. And so now we're getting into some seriously mangled names. They're actually not important. And I'm less than a third of the way through this file. Well, now we're getting into the symbols. RAM and flash are being sorted alphabetically. Sure, good. Scroll faster. No, seriously, scroll faster. We'll be here all day if you don't. Okay. These are just the functions and the variables by name alphabetically, that's all. And now we're going to get them sorted by address. It's truly the same information. It's repeated from other places. This is the third time we've seen this information. There's a lot of stuff here, but you don't need to read the file from start to finish. It's not that kind of document. A map file is a reference book, like an encyclopedia, not a novel. And that is step one to understanding the map files. use them, but don't read them. Don't get too bogged down in the details. Don't worry about all the things you don't know. Figure out what you need and go on. There's a lot of duplication in the map files, which makes it handy to find certain types of memory corruption, but it makes the files seem very long. Okay, so now here at 2098, I have a global variable that's being corrupted, say in my code, and I noticed that it isn't the value I think it should be. Say it's parm buff. So now one of the things I can do with the memory map is look what's around it, see what could possibly happen to my parm buff. We have pin handle table there above parm buff. If it's writing beyond its memory, that might explain the corruption I'm seeing in the variable of interest. Walking through files like this, though, is not the best way to use a memory map. Usually I just searched for parm buff until I found something worth investigating. But that was a very simple map file. Let's look at another map file very briefly. Hello was 2,162 lines long. This next one is for a system that does a lot more, including interfacing with both BLE and Zigbee. It also is loaded by a bootloader, which is compiled separately, so we don't see that in our map file. The top looks similar, and scrolling down, it still looks pretty similar, but I'm not going to go through all of this again. I think maybe we just need to scroll a lot faster. In fact, let's just scroll to the end. This one is 14,034 lines long, much longer than the other, but it's still full of repetition. And really, I want to look at a more interesting map file. Let's look at one for an imaginary chip. It still has memory configuration, as we saw before, and a summary. These are in the middle now instead of at the top of the file. The ordering of map files is often arbitrary, depending on the build tools. Let's look at Ramlandia. We saw BSS and data. We should always expect those. That's where globals go, and that's where our file static and function statics go. Which is which? Well, globals and statics both go into data and BSS. Depends on how they're initialized. Anything with an initializer goes into data. Anything with no initializer goes into BSS and the lake of zeroing, where they get zeroed out. When we look at the RAM sections, we also expect to see stack and heap. Well, we should always expect to see stack. If you don't see heap and you're in an embedded system, maybe you are intentionally not using dynamic memory. Though sometimes the heap is weirdly invisible, it's implied that everything after the end of listed RAM is heap. Or sometimes it's called ESYS or system, or sometimes EBSS, the end of BSS, the end of linker allocated memory. And there are a few things here on my map that you will not see in your project's map file, things that are part of your system. First, there's this ocean of unused address space. We only used a tiny fraction of the addresses out there in the map file that we looked through, the 000s and the hex 2000s. Even those, we only used a small subset of them. But be careful not to put anything in the ocean, or a dragon will get it and your system will probably crash. There's another address space you can use that isn't on your map, isn't in your map file. The port of peripheral registers, timers, watchdogs, SPI, DMA, UART, all those memory mapped registers that you interact with that are hard coded in the address space. These don't show up in your memory map file directly. They're part of your processor manual. Now, across the memory configuration mountains, we have the Flash Federation. Most of that is taken up by code, represented by .text. Why .text? Lost to the sands of time. But at least this is very consistent across different linkers. I have here the forest of functions and orchard of functions with the mirror lake in between. That isn't part of your processor memory, although it can be part of your map file. Functions go wherever they go, depending on your linker optimization. But when we looked at Hello Map, we saw functions laid out in multiple ways, and I wanted to represent that here. The code section also usually has an int vec or reset vec or someplace where the interrupt vector table goes. And sometimes it's at a fixed address, sometimes not. It may be RAM vec and be over in Ramlandia. It should be somewhere, though we can't quite know where it will be or what it will be called. So I want to go to Initopia here. Here we have CINIT, which is the source of RAM's river of initialization, data's river of initialization. All those static and global variables that get initialized, they have to get their initialization values stored from somewhere in Flash. That all gets sorted out before your processor gets to me. It's part of your init process for C and C++. It's called C startup if you want to know more. C startup copies the RAM functions. C startup also copies RAM functions, which can be there for speed. Maybe there are a few small functions that need to run really fast. So let's go on to Constantinia. Well, they're constants, things you mark with the const keywords or strings that are hard-coded. And by marking them with the const keyword, they don't take up RAM and they don't take up boot time to get initialized. I believe I said not everything applies everywhere. RO data is where many compilers, including GCC, usually put the variables marked with the const keyword. Sometimes you have const, sometimes you have RO data, sometimes you have both. And you may never see switch, which is used for lookup tables for switch expressions. The tables will still be built, but they'll get put into read-only memory unless there's a special section where we might have a faster bit of memory to run our switches from. There are lots of these little linker keywords like this, and we usually ignore them. You can learn more about these different data segments from the internet. It isn't critical to remember what each one does. They try to give hints in their names, except for BSS, which is block starting symbol, but really should be blank something something, so that we remember it's full of zeros. In addition to the parts of the system you usually see, you may choose to allocate space to other things like a storage system, a file system, or a bootloader. And depending on your optimization depending on your optimization level and build system, you may see a list of discarded functions in your map file. Those are the linker showing you how clever it is by showing you functions you shouldn't have bothered to write. Oh, and down here, you didn't think all memory mapped registers were documented, right? Now, clearly, I had a lot of fun putting this together, and you can have access to it. It's pretty easy to find, including on the page that I mentioned, and it's at the bottom of almost every slide. Now that we know what's in the map file, let's look at how to use it. We've seen this list of problems and some possible tools. Not every tool works for every problem. So let me go into these a little bit more detail. Let's say you're out of code space. First thing to do is to look at the memory configuration and summary. Does your summary match the expectations you have based on the processor datasheet? How much memory do you have? How much do you expect? And what kinds of memory do you have? The next step is to decide where's your memory going. Looking at the more detailed information, the function lists. Are you short of RAM because you put a library into RAM functions? Is it your code that's large because you have a ton of constants? Maybe it's all those strings you print out to the debug port. Another question to ask yourself is whether it's a new problem. If so, what changed? If you suddenly run out of space, was it because someone used a particular function that caused a whole library to be included? Comparing files does mean you have to keep around the old map files or be able to easily rebuild them. I recommend releasing them with your binaries, but that's just me. And while looking through the map files, we saw functions were ordered in different ways, by name and address. Sometimes they're often ordered by size. And if you're really hitting a wall, trying to find those last few bytes of RAM or code space, sometimes a visualizer can help. The idea is to make a viewer that looks sort of like this. but with a lot more detail. I looked for a commercial or open source tool to show you what one would look like, but I found very little that did what I wanted. Long ago, I made an awk script to parse my map file into an HTML table with cells proportional to the memory used. It was for a Kyle compiler on 8051. I am sure that there will be a visualizer soon for this because it is such a problem, but I have been saying that since 2000. And once you get accustomed to your map file output, you'll see it doesn't change that much. So scripting a visualizer isn't that tough. And once you make friends with your map file, you may not need to. I've added some visualizer links and resources at the end of the slides, but I didn't find any that I would add to my personal useful tools list. And as you go about optimizing, look at the largest consumers first. Look at the things that are taking up the most space and reduce those. Saving 10% from 100 bytes isn't going to help as much as saving 10% from 1,000. You may find some unexpected libraries are included. You can trace through the functions to see where they're called and find out why those libraries are included with the map file. And some libraries are monolithic, included if any function is used. Other libraries are granular, loading only the required functions. Even the C standard libraries can be monolithic so that using a built-in string copy function can lead to a large footprint. Many times you can write a function to replace that library. Other times you'll need to figure out how to work around the limitation. Let me give you some examples to get ideas flowing. Replace floating point numbers with a fixed point representation. Replace printf with a few functions that don't take variable arguments like log string and log with num. Replace strcpy with your own implementation to exclude the strings library. And replace abs function with a macro to remove floating point math library dependencies. You get the idea. And I am not suggesting you do any of those before you know you have a problem. When you do need to optimize, I'm a huge fan of tracking the changes you made and the results they had, because it isn't always straightforward. If you have compile or link time optimizations turned on, your attempts may not go as you expect, at least not until you get the hang of it. So that's how you use a memory map to consider RAM and code space. Oh, I have a question. I have a question here, a question about RAM, about knowing how much RAM is left in the system. Okay, didn't I answer that in the memory map? Oh, I know the question is about how much RAM do I have left when I'm running. I knew that was the question. And I have a sinking suspicion I'm going to have to actually address this one. Let's say this is your memory, your RAM. These are our global and static variables. They have initializers. We know that the C initializers get put into RAM from Flash. Filling them in is part of the C startup process before main happens. And back to our lake of zeroing, also part of the C startup process, the BSS globals and static are initialized to 0. Everything else is shown as unused in our memory map summary. But it's not unused. No. This is where the heap and stack go. For most systems, the heap grows down and the stack grows up, and we hope they never meet in the middle, but I have my suspicions. Once we call main, variables in the function go on the stack. Some variables are small enough they might go into a register, but most variables, especially the big ones, go into the stack memory. We put it on the stack. So let's say we now malloc some memory. Malloc memory goes on the memory we call the heap. As main goes along, we allocate another bit of memory. And we don't necessarily know how the heap is managed. It depends on your C library, but I'm going to pretend it's a pretty naive heap manager, and new mallocs are just going to go right next to each other. Now let's call another function. The new function's variables get put onto the stack. And this will be important soon. The return address to get from our function back to main is put into a register, the return address register, so we can find our way back to where foo was called from, back to main. So let's allocate some more memory, 3 corals, 4 spiky corals. Let's call another function, another turtle. Of course, this represents the variables newly declared variables declared in our newly called function. More importantly, and before that, the contents of the return address register is put on the stack. So the stack has breadcrumbs telling us how to get back to our main function. We'll use the return address register to return from here, and then we'll pop the stack, remove the turtle, take things off and make them usable. And that includes the return address register. Then we get back to main by popping the stack again. So the stack pointer would go back to the first turtle. But for now, we're 3 turtles in. And I use turtles because of the story about the flat earth being on the back of a turtle. But what does the turtle stand on? It's turtles all the way down. The stack is like that. It is stack frames all the way down, each one full of variables and breadcrumbs to find our way home. Okay, another malloc, 5 this time. Another function. I said before, but I feel like mentioning it again. If you had an RTOS, each thread would get its own heap and stack. But threads heap and stack, each thread's heap and stack would probably be contiguous and laid out like this. Though your RTOS may keep track of your stack pointer and cause an exception when you have too many turtles that blow out the stack memory. 6 brain corals allocated. Bwah, ha, ha, ha. Another function, another stack frame. I do feel like I should start playing the Jaws theme. 7 violet corals allocated. Another function, another turtle. And here we are with the last allocation. 8 chunks of coral, of RAM. At this point, we have 0 bytes of memory left. And finally, we can answer the question of how much memory we have left. How do you tell how much RAM you have left? When the heap pointer equals the stack pointer, you have 0 bytes of RAM left. You haven't crashed. This is fine. Like a dog sitting in a cafe on fire, this is fine. You just can't call another function or allocate anything further. If you called another function, your stack would put it into the corals, messing up the data already stored there. If you malloced more memory, you would lose the top of the stack, scatter the breadcrumbs, and not be able to find your way home. In fact, you'd probably try to return and end up someplace random. As we are full up in our memory now, let's free some of those pointers to malloc memory. We still need the last set, but not the 7 violet corals or the 5 flowers or the 3 rose-like ones. How much memory will we get back? 7 plus 5 plus 3 is 13. How much memory do we have now? 7 plus 5 plus 3 is 15 corals. But you can't call another function, and you can't allocate 15 corals. Your memory is fragmented. And this is why many folk avoid heap in embedded systems. If you're allocating and freeing memory in a system without garbage collection, your memory can get fragmented to the point where you have a bunch free, but you can't allocate what seems like a small buffer. And this is why how much RAM do I have left is an impossible question. How much do you have in your heap? Is it contiguous or fragmented? How many function calls deep are you? If we disallowed malloc, disallowed the heap in our system, we'd know how much memory we had. It would be from the bottom of BSS to the top of stack. But we could only fill that with function calls, stack variables, and turtles. If you had a hardware abstraction layer that's like 5 layers deep in your system, that's a lot of stack memory just building up, reaching for the heap and certain doom. There are static tools to tell you how deep your call tree is, so you can estimate your stack usage and keep track of a high water mark that indicates the most amount of stack you've used. Though, if you use recursion, a function that calls itself, then your stack can grow and grow and grow because it depends on runtime circumstances. You can't estimate your maximum stack size, which is why many embedded developers shy away from recursion. So here we are, back to how much RAM do I have in my system? And the answer is not what any of us wanted. But the word ineffable is one of the finer ones in the English language. Let's go back to memory maps, which is what this talk was about before I got distracted. Let's talk about debugging the impossible bugs since we're kind of on the subject. These are the icky crawly ones you worry about late at night, but you can't reliably reproduce on your desk. not the ones where the heap and stack merge. Those can also cause hard faults, but other hard faults, which are where your processor says, nope, you just can't do that. Like when you try to write to null, which in our address space is flash, it's 0, 0, and that's the start of flash, not a place you can normally just write to. Or you can get a hard fault when you try to jump to code that isn't code at all. If you're fortunate and you have a debugging tool attached, you get a backtrace, and that can help you figure out where you were when the hard fault was triggered. If you aren't lucky, there'll be some digging on your part. Maybe from the hard fault interrupt, you managed to write your return address register to a log or serial port before resetting. Then you'll need the memory map file to figure out where you were when things went wrong. And note, you'll need the memory map file of the image you're running. So be careful about your versions. Even with a debugger and backtrace available, having the map file open while you look at the stack and the CPU registers might help you figure out where the code was when things went horribly wrong. And note that searching directly for the address may not work, as the map file lists the beginning of the function, and you need to look around for functions that are near your address, which is easy enough if your map file includes functions in address order. The process is similar with the weird memory errors, which sometimes lead to hard faults, sometimes just lead to random results. If you have a global buffer that's getting corrupted, and you can look in the memory map file to see what's nearby, well, is UART buff overflowing into ADC buffer? Finding corrupted memory near the end of segments can also be interesting. This variable is right before the top of stack. It's getting mangled. Maybe I should see if my stack is overflowing. Figuring out exactly what to do isn't easy. And there's still going to be a lot of trying to make it happen more often, trying to figure out when it crept into the code and general head scratching. But your map file gives you a few more tools, makes it easier to find those flash and RAM addresses to find the root causes. On to firmware updates. As you plan out your system, think about how your memory should look. You need your bootloader here, space large enough for the new version to go into, an updatable library like Nordic soft devices. Where do those go? Is your storage system supposed to stay intact through firmware update? Being able to sketch out a high-level memory map will help you figure this out, where things should be. And the linker file we are definitely not discussing, will cause the linker to place the sections where it thinks you want them. Then the actual map file, our memory map file, can show you where they are. And when working with firmware update, you may need multiple map files when debugging firmware update. There's the new code, the old code, the bootloader's code, the soft devices, and they all have to agree on where they're supposed to go for firmware update to work properly. And finally, possibly inexplicably, the map file can show you how to make your code run faster. First, if your code suddenly starts to get slow, there's the diff with the last known good map file. What changed? It may be too small to see in the map file, so diffing your version control might work better. And yet sometimes you can't see why fabs instead of abs made such a big difference until you see a giant library added in to support floats. Next, look at the summary. Look at those memory characteristics. Did you even know that Flash can have wait states so that every time you read from Flash, to run code or to read a constant, the system just waits for like 6 cycles. But knowing how many wait states each type of memory has will give you options for speeding up execution. By being able to move code to faster memory. For example, you may want to copy a critical function to 0 wait state RAM if that's faster than your normal program Flash. For many optimization problems, if you are overusing one type of resource, like your CPU cycles, and you have another available, you can parlay that into a working solution. And finally, for using the map files to speed up your system, look at statistical sampling. This is going to be a ridiculously brief explanation of a very interesting subject. A statistical sampling profiler runs an in and interrupt and stores the return address, thereby figuring out which functions you spend the most of your time in. Of course, you need a pretty big RAM buffer and some extra code, And you could do this with a JTAG programmer or a system debugger, especially the ones that support trace. But sometimes you can't. Sometimes you have to do it in the field. So once you get a dump of the addresses of the functions that the timer interrupted, you can use the map file to figure out where you're spending all your time. As I mentioned, this is kind of hard, but if you need it, the possibility is there, and you'll definitely need a map file. So that's what you can do with map file and the tools to do it. We didn't use one of those, so I fixed it. Let's look at another map file, one from a different compiler, GCC. Well, not really GCC generated, because GCC is the compiler. A program called LD does the actual linking, and that's what generates the map file we're about to look at. Before we get there, let's look at memory mapland again, the pretty map file, in hopes that you find it amusing while I warn you about the graphic content we're about to see. GNU-generated maps are not pretty. If you thought the ones that I was scrolling through earlier were a wall of hex and nonsense, just close your eyes for the next bit. Not only are these maps tough to read, you have to ask for them specially from the linker. The one I'm going to show is for Adafruit's CircuitPython running on a Arduino Xiao, which has a microchip AT-SAM-D21, an ARM Cortex M0 Plus. It's a pretty complicated system running a Python parser from a file system. It starts with a list of files. Why? But then we go on to more important things. Oh, here's a list of discarded inputs. That's sure something I want to know. Oh, hey, the memory configuration mountains, there they are. Hey, I thought we said we weren't doing the linker file. No, I said definitely not linker file. Why are you doing this? Who's in charge here? Fine, I'll talk about it in a little while. Talk about linker files later. Settle your optical sensor down. Okay, we're in the function forest in the .text in the county of code. And now we're moving on to Constantinia, the RO buffer, the RO segments. These go on for a good long time, as expected in a system of this scale. And now we're starting to get into other stuff, but none of it's very big. So I'm pretty happy just skipping it. Oh, and here's Ramlandia. They don't have any RAM functions. I'm kind of sad. I like those. And all that data along the river of initialization, both globals and statics, here is that data. And we're going to move along, and then we're going to get to BSS with its lake of zeroing, still globals and statics. And here we are getting to the stacks. The stack ends at 2027-34, but the RAM from the memory configuration goes to 2008,000. So we have 5.8cc, around 22K left over. Remember that, we'll need it later. So moving along, we have some stuff that looks important, but who knows? Let's skip those and come back if we need them. Or maybe Google arm.attributes and find out it has something to do with ARM and probably isn't something to mess with, safe to ignore. Oh, now the map file tells us we should load all these objects. I mean, did I really need to know that? Isn't that something some other tools should do? .comment, debug frame, they don't look critical. They aren't huge, we can Google them, but for the most part, ignoring is okay. Yes, the cross-reference table. I guess GCC doesn't think we have search, because here's a list of where every function is defined. I suppose it might be useful if we're getting a function from an unexpected library, but mostly snooze. And that's it. I mean, there was a lot of scrolling and ignoring, but we saw most of what we expected. We didn't see the heap explicitly called out, but the build message on the bottom gives us a little clue about that. The EBSS gives us another little clue about where the heap will be placed. And remember, in order to get the GNU linker file, in order to get the GNU map file, you may have to use a compiler, linker, flag. At the beginning, I promised to tell you a little more about where map files come from. And I've mentioned the linker file, but how does the linker really know where to put all the code and constants in Flash, and that the statics and globals should go in RAM? There's the linker file, which has been on the screen a couple times. It usually ends with command or .make or .ld or link, and explaining them in detail would be a whole nother talk. But let me show you a little taste of what a linker file looks like. This was up on the screen before, but let's look a little more closely and compare the hello example link file with its map file. You can see they're definitely siblings. See how the memory and memory configuration matched? And then we have these sections that we see again later. Those sections go into different types of memory, Flash and SRAM. And I hope you can start to see how this answers some of the questions like, why is our Flash organized like this? Why do some parts of our code go into Flash and other parts into RAM? Because that's what the linker file told it to do. And, oops, that's going to be a problem. This is another area where the GNU tools are pretty much the worst for learning. Their link files are usually much harder to read, with many tools that end up doing exceedingly clever things with CINIT and BSS variables, making them hard to see in the link file and in the map file. According to its man page, the GNU linker, LD, accepts linker command language files written in a superset of AT&T's link editor command language syntax. So, in order for your code to build, an unknown program accepts bizarre files in an archaic language. Our world, our embedded systems are full of wizardry and incantations. And yet, linker files are very important, especially if you're allocating specific sections for some sort of storage, or you have a bootloader, or the ability to switch between application images. Still, you need the map file. You need to understand the map file before you can understand the linker file. The linker files are the directions. The map file is the reality. Honestly, I haven't figured out a way to make I haven't found a way to make linker files fun. My thought, and it really is just a thought, nowhere near a plan, involves a Rube Goldberg machine. I think embedded systems is hard to teach because we jump to so many details. How many of you were shouting tail recursion in the section about stacks of turtles? Yes, tail recursion is awesome, but aren't there fundamentals to learn before we worry about optimizing everything? Between hardware and software, our world is made up of exceptions, tweaky little things that aren't always true, corners we cut to keep costs down. How do you teach things in the right order to show the fun, the technical information, design methodologies, and 100 little details that depend on the processor and application? I don't know. I have been excited to have Arduino be a popular thing, to let people play with the hardware and software, to fall in love with making gadgets. But we need a bridge between play and work. I tend to like metaphors and simplifications, and I spend a lot of time near the ocean, but nothing replaces experience. How do we make it easier? And this is something I would like to talk about further, but I'm about out of time. So thank you for being here. I'm Elecia White. If you'd like the pretty memory map land file for yourself, there is a link on the slide. If you've enjoyed this presentation, you may enjoy Embedded, a weekly podcast where we talk to folks about the how and why of the systems they make. And I'm doing a Making Embedded Systems course through ClassPert based on my book, which doesn't focus on one processor or heavily on code, but tries to give you a framework for what to expect when making embedded systems. The new cohort for Making Embedded Systems through ClassPert starts on March 12th. Well, let's just say it starts in March. Let's not get too excited. For those of you watching now, I have a coupon code good for the next 2 weeks from today, which, I don't know, November 18th, and it's good for the next 2 weeks or the first 25 seats. But the course doesn't start till March. And that's about it. So let's get back to Elliot.
Hey, thank you very much, Elecia. That's fantastic. We're going to work on some questions real quick so you can answer them. There were a few that went out as you were giving the talk. I think the first one actually got answered as you were going along, but Pierce Nichols asked, can the map file be used to instrument which functions are being run? That would be useful for finding the holes in hardware in the loop test programs, for instance.
Yes, exactly.
Yeah. And I think you ended up covering that in one of those sections. So, waiting for some more questions to come rolling in. People are saying your graphics were fantastic, and I have to agree. There's nothing I'm more scared of than the heap crashing with the stack, and you explained those holes beautifully.
Thank you. For most of the art, I used Incarnate.
Mm-hmm.
It's a Dungeons and Dragons style map tool, and it
Okay.
was a lot of fun to put together. As for why map files are so complicated to start with, because they do all these things. That repetition that I talked about, where you have the files ordered in different ways. Well, at some point I said I needed to know what was around the file. And then at another point I said I needed to know how big the files were. And so they reproduce the information trying to solve all the problems they can come up with. Now, I don't know why they ever put it in alphabetical order. That just doesn't make sense to me. But yes, there is a reason they're so complicated, because they do so much. The list of tools, the map visualizers, here are the map visualizers. This is also available in the slide deck, which I've already mentioned is available. Let's see. Statistical sampling from Mike's Dish. And when it's most useful to use that trick? Well, the best way to do it now is to buy something with trace capability and do it on your desk, because it's going to save you a lot of time. But that isn't always possible. Sometimes systems behave better on your desk than they do in the field. And so if you want to know why the field systems are running out of CPU, however you decide they're running out of CPU, but they are clearly CPU limited when they shouldn't be, when they aren't on your desk. That's where statistical sampling really comes into play, where you start with a giant RAM buffer and you put your return addresses in over and over again and you count. You know, I was at this address, I was at this address, I was at this address. And then you take that list of addresses and you go to the map file and you say, oh, this is in delay millisecond, this is in printf, this is in, oh, that function I really meant to take out before I shipped it. And so I wouldn't do it for normal profiling, because there are tools that are better than statistical sampling, but those tools don't always work in every case. These are terrible questions, people. But thank you. I really do appreciate what you're saying. It's very nice. It's very kind of you to say. Do you want to see the map file again? That's probably the best slide I have. So that's the pretty map. And now I've discarded it.
And then I also pinned the link to this file in the Discord general channel for people that are in there.
Let's see, RAM funcs. RAM funcs appear in both flash and RAM memory segments. Under what conditions would a function be put into RAM, and is there a way to know in advance where a function will be put? Functions are put wherever the linker file tells them to. The reason you would put a file into RAM would be if your RAM runs faster than your flash and you need to run fast. You can also, there's also bootloader reasons to do that, but I don't want to talk about those. And so what happens is your function gets compiled to flash. I mean, it gets compiled and then it gets written to your flash. And then on C startup, flash says, oh, I have a RAM function. I'll have to copy this whole file, or this whole function over into RAM, because all of the other places, all of the other things that call this function point to a place in RAM and not to the place in flash. Does that make sense? Does somebody want me to do that again? I can only see Elliot, so if he's not nodding, I don't know what you're saying.
I'm okay. Nobody's typing.
They're all typing.
That's true.
No map visualizer does what you want it to do. What would be points on my wish list? I want the ability to look at RAM and code separately. A lot of them right now are combining, but usually you're having one problem or the other. I want to be able to have proportional sizes so I can visualize and say, oh, that's where most of my memory is. I want to be able to mark off bits and say, I can't change that library. I want to be able to have it look nice, which is hard because you have a little tiny function that's only 15 bytes long and you're comparing it to a monstrous function that's 2 kilobytes long. And how do you put those in the same visualization? You can use logarithmic methods, but then you're not really being true to what it's saying. If you want to talk more about that, I would be happy to talk more about what I want in Map Visualizer. But the high level answer was that was the one that I had up. Let's see, the one that I said was kind of like your processors. Okay, I just should have started at the beginning because that's where it is. This is a very long presentation. Thank you for sticking through it with me. This one, I want it to look kind of like this, where I can see the different kinds of memory and I can zoom in on certain parts. It's still sharing my screen. Yes. Okay, good. What about self-modifying code? Part of me is like, don't do that. The other part of me is like, that's a bootloader. Yes, of course we have self-modifying code. Would you put that in RAM functions? Yes, but I hope you know what you're doing because I don't. But we do have, we put things in bootloaders and then we modify our flash. And that's self-modifying. And sometimes the bootloader needs to go in RAM so that we can erase all of our flash. And sometimes the bootloader can be snuck into a part of flash, a page that doesn't need to be erased. What is the coolest debug you had to do with map files? That would be at Leapfrog, where software was cheap and hardware was hideously expensive. So every single byte was just, you had to wring it out. And that was where I did the visualizations so that I could, because we had a fair amount of flash, but RAM was always low. And if you could figure out where it was going or how to cheat so that you were using flash memory instead of RAM, it was very helpful. And when I say flash on that, I actually mean ROM, because toys don't have flash. They have read-only memory that gets programmed in masks that probably somebody here will be talking about. It'd be very cool. The chips that don't have flash and big consumer problems.
All right, thank you very much. We're gonna take a quick break, I think, but will you be around to stick around in the Discord for a little bit if people have some more questions?
I will, absolutely. And I may have some questions for some other talks because you have an excellent lineup today. And
yeah, I'm excited to see the rest of it. Thank you.